Hello physics students, and welcome to our second video in this unit. We're going to look today at Newton's first law, what inertia means, net external forces, mass and inertia, and equilibrium. So what is Newton's first law? Actually, it's kind of interesting because in the late 1600s, Newton developed this first law of motion. However, in the early 1600s, Galileo had realized a very similar idea when he slid a block on a perfectly smooth surface. He realized that that block actually could slide forever in the absence of an opposing force. And so he actually came up with that idea that it is an object's nature to maintain its state of motion. But Newton summarized it very nice in his first law of motion, stating that an object at rest remains at rest and an object in motion remains in motion with constant velocity, constant speed in a straight line, unless that object experiences a net external force. So if Newton's first law is true, if objects tend to resist change in motion, will an object with no force acting on it always be at rest? Well, that's not necessarily true. If the object was already in motion, it will continue to remain in motion unless an external force acts on it. This is just an interesting idea when we think about this. Why then, here we have the marble is speeding up down the ramp, and when it's going up the ramp, it's slowing down. Why does that happen if what we're saying is true? What's going on? If we remember our force diagrams and we look at the forces acting on these objects, we can see why. In this first case, where the the ball is going down the ramp, we have a force right here exerted by the ramp on that ball. We also have the force of gravity being exerted directly down. The motion of the ball is going forward. We can see that the ball does not have balanced forces here. We have more force in this forward direction than we do. They do not cancel equally. And likewise, in this situation, we have the force of the ramp is this way, whereas the force of gravity is this way. So we have more of a backward direction for our net force on that. If you would do the math, then that makes sense why this ball is slowing down. In this case, the force from gravity and the force exerted up by this plane, this flat plane, would be equal. So we do not have any changes in the net force in the vertical direction. If this ball were already in motion, it would, if there were no friction involved, the friction would obviously be going this way. If there were no friction involved, however, then this ball would, on the bottom, would continue to move forever. Its velocity would not change. So an important concept is that inertia, right here, is the word that we use to describe that. I know you've probably already heard of this word. The tendency of an object to resist change in motion. It maintains its state of motion. So when we're talking about Newton's first law, sometimes it's referred to as the law of inertia, because it states that in the absence of forces, an object will preserve its state of motion. Another way to think about it, or to say that, is that when the net external force on the object is zero, its acceleration, or its change in velocity, is also zero. So when we're comparing these different objects, which has more inertia? Remember, inertia is the ability of an object to resist change in motion. So it's already moving, it would resist any change in that. It would not want to, it would resist moving faster, it would also resist moving slower or stopping. So this object or this object, which has more inertia? And you'd be right if you said the one that has greater mass. You know that too with these vehicles. This obviously has more inertia. It has a lot more mass. The greater the mass of an object, the less it will be able to accelerate under an applied force. You know, it takes a much greater force to accelerate this object than this object. Similarly, a less massive object, one that has less mass, would undergo larger acceleration than one of greater mass under the same force. So if you applied the same force to this object and this one would accelerate more than this one. Same with these. So when we talk about the amount of matter in an object, it is also a measure of the inertia of that object. So here's another example of how mass is a measurement of inertia. If you think about a bowling ball and a baseball, if we have the same force that strikes each ball, you know that this large bowling ball, very massive bowling ball, experiences a much smaller acceleration. It has more mass and more inertia. So inertia is proportional to mass, and mass measures the amount of matter in an object. It also measures the inertia of an object. So we've thrown around this term net external force. Let's take a look at specifically what we mean by that. The net external force is the vector sum of all forces acting on an object. In other words, it would be the resultant force vector when we add all the different forces. If we just conceptualize the four different forces here acting on this car, we have the force of the ground on car going in this direction, the force of gravity in this direction. Here's the forward force. This would be the force of resistance, air resistance, friction from the road operating in this direction. The acceleration is going to be determined by this net external force. So this vehicle cannot change its motion unless the net external force, there is a net external force. If there is no net external force, there would be no change in the velocity of this object, which means there would be no acceleration, either positive acceleration or negative acceleration. It would not change its motion in any direction. If this object were to be accelerating in this forward direction, this force would need to be greater than the force of the resistance. Another example of this idea would be this little tug-of-war contest with these kids. When the boys and girls pull with equal but opposite forces, this center ribbon is at rest. When the girls apply a greater force, the center accelerates to the right. So let's try a little problem where we apply some of these ideas. Here's our problem. A student leaves his physics book on top of a drafting table. And drafting tables are tables that are at an angle. It's at a 35-degree angle. The free body diagram here shows the forces acting on the book. Find the net external force acting on the book and determine whether the book will remain at rest in this position. First, let's identify our variables, and I'm not going to rewrite these because they're written right here. The force of friction, 11 newtons. This angle, force of the table on the book, 18 newtons, and the force of gravity on the book is 22 newtons. My net external force is unknown, and that's what I would like to find. Find the net external force acting on the book. The next thing we need to do is to select a coordinate system. And I'm going to select a coordinate system that makes my life the easiest. So I'm going to select one in which the x-axis is right along the plane of the table and the y-axis is this direction. That sort of maximizes my vectors that are directly on the x and y axis, because if I select this as an axis, I have this vector that is parallel with that, and then this axis, this vector is parallel with that. Now remember, from here, what I'm going to do is I'm going to be adding each of these force vectors together, because that is the net external force, is the sum of all of these forces, vectors, right? And forces are vectors. So this one I will determine the x and y components, and for this one I will determine the x and y components. This is the only one that is going to be a little bit more difficult, and I'll have to think about the x and y components on that. So here are my x and y components for the force of friction. X is negative 11 newtons, because it's in the negative direction on the x-axis. Y is going to be 0 newtons. The force of the table on the book, when resolved into x and y components, will be 0 newtons in the x direction and 18 newtons in the y direction. Now let's focus on the force of gravity on the book. This one, the x and y components, we're going to have to determine using some of our trig functions. I know that the force of gravity is perpendicular at a 90 degree angle to the surface of the earth. So I can obtain a 90 degree angle there. I know this angle because I was given this in the problem. Theta, in this case, is 35 degrees because we know that the drafting table is inclined at a 35 degree angle. Now, if you'll notice at this point, I'm really not able to resolve my force here into its x and y components because I know this angle, theta, but I'm not able to know this component and this component of it. It would be a lot more helpful if I knew this angle. If I know this angle, I can then draw a line here perpendicular and I can resolve my x and my y components of this vector more easily. So in this case, I'm going to need to know that the sum of all the angles in a triangle is 180 degrees. If I know this is 35 degrees and this is 90 degrees, I know that this angle right here, and I can call that theta prime, theta prime is going to be equal to 55 degrees. At this point, I'm going to go to the next screen and redraw this so that it doesn't get confusing. So here I have theta prime right here is 55 degrees. I have this force vector is 22 newtons. I would like to know my x component of that vector and my y component. This line is drawn to be 90 degrees to the x-axis. So I can set up some of my little trig functions to figure out what the x component is for this force. Cosine of the 55 degrees, cosine of theta, equals this side, which is the force of gravity, and the x component force of gravity, divided by the hypotenuse. In this case, it's 22 newtons. So my force of gravity in the x direction is 13 newtons. I'm just going to write this over here. X equals 13 newtons, and we're going to figure out y next. I know that the sine of theta of 55 degrees is going to be equal to the force of gravity in the y direction divided by 22 newtons. So my force of gravity in that y direction is equal to 18 newtons. And I'm just going to go ahead and write down the y component of this vector is 18 newtons. Now I can take the sum of all my forces in the x direction. And that's going to be negative 11 plus 0 plus 13 newtons. That gives me a total of 2 newtons. Now I can take the sum of all of my forces in the y direction. I have 0 newtons. I have a positive 18 newtons here going in this direction. This number here is actually negative 18 newtons because the x is positive, the y is going to be in the negative direction. So we have a negative 18, minus 18 newtons here. And so the sum of all of my forces in the y direction, in this case, will be 0 newtons. So in this case, this is very easy. We don't even have to think about adding these up and using the Pythagorean theorem or trig functions. We simply know that the sum of these vectors is 2 newtons downhill this direction, 2 newtons in the x-axis direction as we have set it up, which means 2 newtons downhill on that table. In other words, if that is our net force, and I'm just going to rewrite this here as our answer, our net force that we've determined is 2 newtons downhill, then will this physics book slide? Yes, it will, because we have 2 newtons of force being exerted in that direction. That is our overall net force that we've added up, so the physics book will slide down that table. And just a simple application, you all know that Newton's first law explains why we need to wear our seatbelts in the car, because objects in motion tend to stay in motion. Here we have a picture of, we had 2 objects in motion, the dummy and the motorcycle. When the motorcycle comes to an abrupt halt because of the force of this car, the dummy continues to stay in motion and be projected forward. Seatbelts, therefore, keep the objects or the passengers from continuing to move in a car crash. Something you could investigate. And there's a good explanation in your book. Look in there and look at how the mechanism of a seatbelt works in a car crash. That could be some advanced proficiency for you. So one last item to present here in this video is the idea of equilibrium. Objects that are either at rest or are moving with constant velocity are said to be at equilibrium. So in order for that to be true, you know that if objects are in equilibrium, the vector sum of all the forces acting on that object have to equal 0. And then we can say that object is in equilibrium. A mathematical way to say this, and remember that the sigma, this is a sigma, it means the sum of whatever is following. So if the sum of all of the forces in the x direction equals 0 and the sum of all the forces in the y direction equals 0, then that body is in equilibrium, that object. The previous example of the physics book on the drafting table was not in equilibrium because the sum of these forces was not 0. We had the forces in the x direction were 2 newtons, and therefore that was not an object in equilibrium. Newton's first law, in essence, describes objects in equilibrium. Objects in equilibrium tend to remain in their whatever state of motion they are in. If they're at rest, they will remain at rest. If they are at some constant velocity, they will remain at that constant velocity. Here is an example of an object in equilibrium. Its forces are balanced. The forces in the x direction, the sum of all the forces in the x direction equals 0, and the sum of all the forces in the y direction equals 0. We have drag and thrust for the x direction. We have lift and the weight, force of gravity in the y direction. Its airspeed is this way. The airplane is moving in a straight line at a constant airspeed, therefore the forces are balanced and it is in equilibrium. So a quick review, these are the things we've discussed in this section. And again, if you want to do some advanced ideas, look at how the mechanism of the seatbelt in a crash works. You could look at other things too. How does a hovercraft function? Anything that's not mentioned in the video that sounds of interest to you, that describes forces, and any of these topics we've discussed, look into that, and I look forward to seeing you in class.